And so it's a series of works with Pierre-Louis and Benoit Pertam and a young, in several combinations, a younger person in Leipzig, Benjamin Guess. So let me try to describe the problem. It looks very complicated, but the easiest way to think about it is you have a scalar multi-D conservation law. So when I put boldface there, I do it in order to denote a vector. And it's driven by a rough time signal. So think of B as being, if there is no x dependence and nowhere differentiable function, that's why I write it as dB. Or if you like, think of it as consider it a Brownian motion, and some of the results I'm going to describe will hold for B being a Brownian motion. If B is, of course, just T, then you have the classical deterministic problem. And when B is a Brownian motion, this action of A on dB should be considered in the Stratanovich sense, and I will mention later on what it means. It's an extension of even in the deterministic case, of the general theory, because the existing theory works with scalar A. Here we can allow a system because of a particular application we have in mind. And always as a thing to remember, the canonical example is a stochastic Burger's equation. All right, so eventually I'll learn how to do that. Okay, so this is an outline of the talk. I want to describe a notion of solution. I mean, that's part of the problem, and describe that is well posed. So we're going to call that pathwise entropy or kinetic solution. I want to discuss its long-time behavior and convergence to possible invariant measures. I want to talk a little bit about phenomenon like regularization by noise, and conclude with, if there is time, with an example where we have convergence of approximations, and mention some open problems. Okay. So why did we start working on this thing? At the beginning, I have to admit, it was mathematical curiosity. In the process of developing with Pierre-Louis the notion of the stochastic Hamilton-Jacobi equations, we realized that the ideas we were employing there could be used to study conservation laws, and then we left it in the back burner together with many other things. So that was the first motivation. The second, and of course, if you are in 1D, the two problems are somehow equivalent, although the techniques are different. Then we were interested in the problem to detect some possible regularization by noise results, like averaging lemmas, and whether they improve if you include stochasticity. There are several applications of these models in phase transitions in random media, randomness in oil exploration, or whatever. You can think of any time you have a conservation law adding a stochastic term. The concrete application that we have is something that Pierre-Louis has, I think, talked about it. He told me in one of his many videos. So it's about mean field gains. And it turns out that if you, oh, come on. If you take this stochastic differential equation in RD, where the diffusion depends on the particular agent and the average of the rest of them, so it's symmetric, and you look at the law that characterizes this stochastic differential equation, then as L goes to infinity, the number of agents goes to infinity. The law converges to a probability measure on the space of probability measure, and it's moving according to this rule, and the density function satisfies this stochastic conservation law. So the I shouldn't be there. And this is now a matrix, that matrix there, the adjoint of that matrix. And that's a canonical example of the kind of models that come up, and they are of this nature. Okay? I apologize for this. It's completely counterintuitive, the thing I have. Okay, now let me review a little bit the deterministic theory and explain what are the new things that one needs to do the stochastic case. So here, the only thing I'm doing is I'm writing down the problem, simple case without x dependence, and I'm taking the noise, the B to be a smooth path, so I don't have to worry about writing dB. then one of the things we learned very early that for such kind of problems, the best way to try to solve them, at least initially, is to use the method of characteristics because it's a first order equation. And for that problem, the characteristics are basically these two ODEs. X, which will give you the location, is solving that ODE. And because I assume no x dependence, z, which is supposed to be the solution along the characteristic, is constant. So the solutions are constant along characteristics. And of course, one would like to invert that function there to find u. It's well known that that creates shocks, and this is a picture from Evans's book because it was convenient. If you take Berger's equation, which is the canonical model, and you start with an initial condition that is the characteristic function in the interval 0, 1, then, and you try the ODEs here, the system of characteristics is just x dot equals z, z dot equals 0. So the solutions are constant along z, and say you see if you start past 1, there z is 0, so the characteristics go straight up. If you start less than 1, the characteristics are up and going like that. If you start between 0 and 1, the characteristics move with slope 1. So they go like that, and they intersect with these characteristics, so that's the shock. And then for this particular example, you have to figure out how to propagate, how do you fill the space between there. And that you do using refraction waves, which is a smooth funnel of waves that goes like that. And if you don't do that and you try to put a shock in between, you have non-uniqueness. So that's the problem. So the choice between refraction waves or using other characteristics that cross is the one that creates the non-uniqueness. So discontinuities decrease as they're propagating. And the other thing I want to make, because I will make a comment about that later on, is that solutions are not reversible in time. So if you are at that point, you don't know whether you go there or there. And that will play a role in what happens later on. So this is the problem, solutions that are not differentiable or anything. And the correct way to study this problem, and that goes back to Lax and Fermos and others, was to introduce the notion of entropy solutions, which formalized by Kruskov looks like that. U is an entropy solution of the problem if the following inequality holds for any S that is convex and any Q that you get it by solving this, any Q that has antiderivative of that function. So if you have a function U, which a priori is in a bounded measurable function, let's say, or in L1, and you can justify this inequality in a weak sense for any convex entropy, then this thing is unique. The inequality, the best way to see it is to consider here a viscosity approximation, try to make the change of variables, and then you're going to get a term which will be like a minus S double prime UX squared. And the only thing you can do about that is the sign, and you drop it, and you're left with that. OK, so what Kruskov did, he used a particular entropy, this function U minus K. And so the definition, what I mentioned up there for that particular entropy, means that this thing has to be greater or equal 0 for any non-negative test function. And this is the flux. This is the entropy, yes, and this is the flux. And then doubling variables and using appropriate approximations to the identity for phi, he was able to prove that the solution is well posed. Doubling variables means here you if you have two solutions, you use uxt here, and for k you use vy tau, and you integrate 4 times, and then integrate by parts, whatever you can, use the cancellations, and you can get a uniqueness result. OK. So an alternative to that, and this is what we are going to use for the stochastic entropy solution, is the kinetic theory. And I assume in France this is taught in high school, but just in case someone missed it, let me remind you what it is. Let's assume that the initial data of the problem is non-negative, in which case the solution is non-negative, so I don't have to write 2 things. I can write only one, and define this new function, which is the characteristic function of the interval 0 xt, u to xt. So that's a Maxwellian of the problem. And then the question is, try to find what is the equation satisfied by chi. Right? So I'm sorry if I bore you. Let's do it in 1D, everything assuming smooth. So you take derivatives, you play with Dirac masses as much as you want, and then at the end you find that dt chi is equal to minus a prime psi, and the derivative with respect to x of chi times b dot. The b dot is nothing there. Okay, so, and that's the kinetic formulation. So we say that they say that the solution is a kinetic solution if it satisfies, if the function chi that corresponds to that solution satisfies this linear equation. And the caveat about having the non-negativity before is the right-hand side is the derivative in psi of a bounded measure, of a non-negative bounded measure. So that's the kinetic formulation. It is much cleaner because instead of using any entropy, you can use a particular one. You use only one function. Of course, it doesn't take much to see that if you have that inequality and you multiply by a convex entropy and you integrate in psi, you reproduce the previous definition. The advantage of that is that it's a simple equation to write down, and it has a very robust form that we can use to study the stochastic problem. Okay, so now we recall that, and let me describe what are, I think the speed I go, Pierre-Louis will come and go. Will be over by the time he comes. Anyway. So the main difficulties for studying this problem. The first one is even how to write it down. Anything I wrote down required, I said assume B is smooth, but if I look at the actual problem, B may be nowhere differentiable if B is a Brownian motion. So like in the theory of stochastic differential equations, to understand that, you have to understand it in an integral form, but then you have no regularity. So point-wise definition is out. You cannot write inequalities because, again, with something that like B that changes becomes plus minus infinity, it's very hard to interpret inequalities in the stochastic case. It's not possible to, I mean, one attempt to do this problem is to say at least when we are in 1D, just do a rescaling in time. And of course that will fail because rescaling in time will fail because rescaling in time, it will mean that you can find a universal time-independent problem, let's say like that, and the solution will just be that solution evaluated at a new time bt. Formally, this is correct. That satisfies this equation. The difficulty, of course, is you have shocks. And the shocks, as I mentioned, they are not reversible. So for a short time, before you have shocks, it will be OK. But then to solve that, you have to solve it forward, backward in times, and you are going to have a problem. So change the variables, it will not work even in 1D. Then the next question, of course, if you study stochastic partial differential equations, is to use the classical martingale approach, which, okay, I'm recorded, I cannot say. For me, it's some kind of sophisticated integration by parts thing on the right space. Unfortunately, it's not going to work, or we don't see how to work, and we don't believe it should work. And here I have tried to explain to you why. If you have a stochastic differential equation, we also learn in France in high schools that solving that equation is the same as solving this partial differential equation. The dots are there because I keep writing Stratanovich there. So if you solve this, if you know how to solve this equation for any initial data, that's equivalent to knowing the law of that stochastic differential equation. So now let's start, and instead of a stochastic differential equation, we have a stochastic PDE. So the x now is a partial differential equation here. And then if you think of the analog to that, then the law is going to be characterized by solving a partial differential equation in infinite dimensions. And here you have a second order operator in infinite dimensions, and you lose all kind of compactness that you can have to apply the martingale theory. So we don't think that this can be done. On the other hand, here's a very simple observation. Let's take the x-independent problem. Look at this family of problems where B epsilon now is a smooth approximation to B. So take B modified. B is a continuous path. Do a smooth approximation, just modify it. And then the following thing happens. You have the solutions for the smooth B epsilon are bounded in L1. Oh, okay. I thought I was going to finish before you came. They are smooth in L1, and also if you assume BV initially, that's why I'm assuming that U is independent of X, you have L1 and BV bounds. So along subsequences, you have a limit, and the question is there an equation that the limit satisfies? What do you say about the limit? All right, so these are some of the difficulties. Now, a little bit about Sratanovich versus Ito. If we could make sense out of that, the claim is that for the problems we have here, if you have a theory in L1 and you have a forcing term, that a signal that multiplies the nonlinearity, it's better to use Sratanovich because here's why. If you take two solutions, you subtract them, multiply by the sign, and integrate, you see that, okay, here I'm assuming everything is smooth. You see that that term that multiplies the bad noise goes away. And so it's better to having multiplying like that. And of course, if you have that for smooth things and you pass to the limit, you're going to get Sratanovich. It's a basic fraction probability. On the other hand, if you decide to work with a signal that multiplies the function itself, so semi-linear dependence, and here I drop the A because it doesn't make any difference, and you try to play the same trick, you come down to subtracting two solutions, you come down to that, but now there is no sign anymore. On that, no, I'm sorry, it's not a question of sign, there are no derivatives there anymore, so when I integrate the x, I'm not going to have any cancellations, and that's why for problems of that form, it's more convenient to use Ito's, the Ito's formulation, because you can handle it. Okay. Do I want to talk about that? No, I think let's skip this, and let's go to related works, and then I come back and talk a little bit about the, I try to introduce the notion of solution. So stochastic perturbations of linear transport equations, where you see some kind of regularizing effect. Again, everybody here knows how to study the good theory for ut plus divergence bu, and you know that you don't have regular solutions. If you add a noise here, then immediately you get a regular solution. So that's one thing. There was a large body of work by Wen and E, Kanin, Sinai, in many combinations to study the Burger's equation, let's say, with a random forcing, and they wanted to understand the structure of shocks and so on. There is an even larger body of work for semi-linear dependence. Remember, this is what I tried to say in the previous transparency, that study these equations in Ito's formula, in Ito's form. There was the work I mentioned with Pierre-Louis about stochastic Hamilton-Jacobi equation. In terms of long-time behavior that I'm going to discuss, again, there was work where you have a quasi-linear equation, and the right-hand side is Brownian motion. And then there was the issue of the long-time behavior of deterministic conservation laws, where some of the things I'm going to say here apply to that case, and I will give more references later on. Then, as far as the semi-discrete schemes we are trying to use, it's some version of, they go back to Brenier and Giga and Miyakawa and Vasseur. And I should mention a most recent paper by Deia, Kubinelli, Hoffmann and Tyndall, who derived, the paper is, I haven't read it, but the claim is that using rough paths, you can reconstruct the same kind of solutions we have here. All right. Okay, so now I want to describe to you the idea, how one writes the solution. So the idea, as I said from the beginning, was try to employ what we had done with Pierre-Louis before about stochastic Hamilton-Jacobi equations. And of course, that I know this is not very illuminating the way I'm describing it. The idea there was to deal with nonlinearity by we wanted to do some kind of viscosity theory. So we were using test functions which were adapted to the operator, and they were basically, we were inverting the characteristics on the level of the test function. So that's what we want to do here, and that's what we are doing, but the test functions here come in a more complicated way. So let me go back to that and write down the kinetic formula. This is the kinetic formulation. And mu is a non-negative measure, as I mentioned. And these are the characteristics that correspond to that problem. And now, in the Hamilton-Jacobi case, the difficulty was that the problem was nonlinear, so we really had to invert characteristics, which exist only for small time. Here, this is a linear equation, so we can write down the system of characteristics, the equations for the characteristics, and just eliminate that term. So this is equivalent to that. So the PD is gone, and what you have is information about the total derivative of chi moving along that path. Now notice, any difficulty you may have had with B before not being differentiable, it's gone now because B is smooth. I mean, B is continuous. But there is a small difficulty when you do this, because now the right-hand side is not anymore the derivative of a measure, is the derivative of a measure evaluated there, and is not a full derivative. Therefore, this idea of integrating by parts and getting rid of this because of sign doesn't work. And the problem is, how do you handle that term? So let me show you how we can do that using the characteristics. So a trivial computation. I'm rewriting, assuming that B is smooth, I'm rewriting down the definition of that. So you multiply by a smooth function, integrate everything by parts, and you get this. And if I stop here, I have the same problem I had before. I cannot, if I try to eliminate this term, will pay. So instead of using this particular test function, let's be smarter. And instead, start with a given test function, but use as phi the solution of this linear, with no forcing term, first order equation, which can go forward, backwards, and there is not an issue of invertibility or whatever. So the solution of that equation is given by this form. Okay? It's exactly what I wrote before, but now there is no measure on the right-hand side to pay for it. And so now what you do is multiply this by phi, multiply this by chi, put things together, and you see that you have a full derivative in the product chi phi. You have a full derivative in space in the product chi phi. On the right-hand side, we have the original measure, m, applied to a smooth function phi. So we don't have the problem we had before. This is clean now. So if you integrate, what you find is that this equality here, where with the phi is the one that moves along characteristics. And we're going to use this as a definition of the solution. As a matter of fact, in the case where B is smooth, that's equivalent to the entropy solution. And that's the way we're going to define a solution. So this is a pathwise formula. It doesn't depend. Remember, the phi is of that form, but we are integrating out in psi. So the only thing we use is that B is continuous. And this is what we're going to use as a definition of the solution. And the regularity of B is irrelevant at this point. OK, so here are some results. Using this as the notion of solution, we can prove that there is a unique solution, and it satisfies a contraction property in L1. We have explicit estimates on the dependence on the noise, on B, for the homogeneous problem when there is no X dependence. And so solutions that correspond to different B's can be estimated by this term. So, and I want to bring your attention to that term here. This is not a pointwise anymore property in S. This is, for every time T, is the sup of the difference of the path of the signals up to that point, which is another way to also see that there is no simple way to transform the problem by just making a change of time. So the whole path, the history of the path comes into there. OK, there is nothing like that available for the homogeneous case. The stability follows by just considering smooth approximations and passing to the limit, because we have BV bounds. For the inhomogeneous case, we have to go through weak limits because we don't know how to obtain any other bounds on A. And we don't know that we have an explicit continuous dependence on B. And applying these ideas, I think one can, and we use that in the process of these theorems, there is a way to simplify, to improve some of the estimates that are known in the deterministic case that were obtained by Dalibard. Okay. There is no way to show the proof or even an idea of the proof. It's based on the proof that Benoit had for uniqueness for entropy solutions using the kinetic formulation, and it's one of these proofs that works because there are a lot of things you can do if you have functions which are take value 0, 1, so their square is the same as that, but it's you do it and it works, and it's hard to write all the technicalities here. So now I want to talk a little bit about the asymptotic behavior and regularizing effects. And let me do a caricature of something. I start again with the Burger's equation, and that's the picture I show you about the shocks. Now, let's do the same problem, where B now is something like that. So B takes values plus minus 1 at certain times. And I want to write down for you, for that particular U, how the shocks look like. So again, that's the interval 0, 1 here. And it's explicit computations. You start computing the characteristics. You see they are different. They look. All right. So I think I give the talk like that and get it over with. The characteristics here are different, start moving in a different way than there. So, and the solution comes down like that and moves up like that. So you see there is some kind of oscillation going on the solution due to the fact that the B now changes sign. So that's a caricature of the problem. Here are some more sophisticated pictures that Benoit allowed me to use from one of his talks. I really have a hard time to say what I mean because he only gave me the pictures, he didn't. But it's the numerically computing what I mentioned before. You have a B that takes a plus minus 1 with probability 1/2, and this is pictures of what you get as, from different omegas and different snapshots. So you see the shocks, you start having something about the shocks and going in and out, and perhaps there is this hope that when you average over all omegas, that something will become more regular. And we will see that in some weird examples that this is indeed the case. Okay, so now let me go to talk a little bit about the long-time behavior of the problem. And the results we have will apply both to deterministic, and they are new for both the deterministic and the stochastic case. So for these examples, B is indeed a Brownian motion when we look at the stochastic case. We work on the torus, and the result you want to prove here is that as t goes to infinity, the solution goes to the average of the initial data, and if possible, to obtain a rate for that. In the stochastic case, you can be very ambitious and call that an invariant measure and prove that the process you are defining has unique invariant measures as t goes to infinity, but let's not use this heavy language because that's what one proves here. So let me give you a little bit of a history about this problem for the deterministic case. So the first result was proved by Lax many years ago, where he used in 1D and strictly convex data. He used his formula, which is an explicit formula, and from there he was able to show that the solution indeed goes to its average with L infinity with rate 1/2. Many years later, Enquist and E extended the result of Lax in 2 dimensions for the strictly convex flux, and they proved the same thing, again with rate -1. Then the next results are in the case where for higher than 1 or 2D, and A's that are genuine nonlinear, and I will say something in a minute about genuine nonlinearity. Results were proved about convergence now without a rate to the mean as t goes to infinity, and there is a first Chen and Fried, and Benoit and Chen, Debus and Vauvel did something, and the most, I think, elegant and general proof is due to Dafermos, who proves that as long as you have a nonlinearity, genuine linearity at a single point, you can still obtain the convergence at infinity, but no rates for these results. In these cases, I think the result follows because you have enough compactness from averaging lemmas to let t go to infinity. And if you try to do the same thing for the stochastic PDE, you don't have this compactness. So the only way we thought about proving convergence as t goes to infinity is to do it in a quantitative way by controlling errors that we make and try to get the rate of convergence. And so it was not that we were looking for it, but this is the only way we could bypass the lack of averaging lemmas and compactness. And in doing that, we were able to obtain a rate of convergence in the deterministic case for more than 2D, which was open problem given the history I described there. So now I want to say a little bit about the genuine nonlinearity assumption, because we introduce a different assumption for the stochastic case. So that's a little bit heavy in terms of notation. The genuine nonlinear assumption, it's necessary. You cannot expect, if the problem is linear and you put oscillations initially, the oscillation will propagate, so there is no way you can expect anything happening at infinity, so you need to kill the linear case. And in the kinetic theory, one way to do that is by measuring the measure of the set where the solution looks like linear. So in this case, what we're going to say is that we have this vector A prime, which is the derivative of our flux, and we introduce this crazy notation. So we multiply component by component with any sigma in the unit sphere. So that's a vector, and we compare it to another vector in RD, and we are making the assumption that the measure of the real numbers for which this thing is less than epsilon decays like epsilon to the theta. So that says that if A looks like linear in psi, the set of that has very small measure. So that's an assumption, and I will describe in a minute what it means. So this is different than the canonical assumption that was used from the beginning by Pierre-Louis and Benoit and Tadmor and others in the kinetic theory, where they were taking the inner product between the vector and they were taking the inner product between the flux, the derivative of the flux, and sigma, and they were obtaining that. So let me talk a little bit about these two conditions. Of course, 2 implies 1 because of the obvious inequality you have there. On the other hand, and of course, and when A is strictly convex and D is 1, the theta is 1. However, 1 is strictly weaker than 2 when you are in more than 2D. So let me show you this example. Suppose you take a homogeneous flux, which is the same in each component. So it's psi to the L plus 1. Then the derivative is like psi to the L, psi to the L. You see that this flux doesn't satisfy this the classical general linearity assumption, because you can choose a particular vector field and a sigma, and you can see that the measure of the set where this thing is less than epsilon is infinity. However, this is not the case with this assumption, which satisfies the second one. So what we are assuming there is a strictly weaker assumption than that. Notice that when, if you are in the classical general linearity condition, there is an upper bound on theta, which is like 1 over d. The reason I'm spending this time about theta is it's going to come in the rate that I will state later on, while if you are in the other condition, the theta is independent of the dimension. All right, so this is now the results we have. So we in the deterministic, in both cases, we are going to assume that the flux grows like psi to the m. In the deterministic case, we are going to use the classical genuine linearity assumption, entropy solution of that problem, and the result is that it converges to U bar at a rate which is t to the minus theta over 2 plus theta. Remember, theta was the measure in the general nonlinearity assumption. Of course, when theta is 1, the rate is t a third, while we know from the results of Lax and E and Enquist that they get a better rate, 1/2. So we make no claim of optimality on the way we get the rate, about the rate. Similar thing in the stochastic case. Now we assume the other condition I mentioned. And here in expectation, the solution converges with rate that is like t to the minus 3 plus theta. And for that proof, and that's why we can use the weaker general linearity assumption, we are using the fact that we are dealing with a Brownian motion. So again, when theta is 1, the rate is minus a quarter. We don't claim anything about optimality. And we attribute to the difference between the rates, here is a 2 and that's a 3, to the fact that the scaling of the Brownian motion slows down the characteristics. And that's why we get a different rate here. I may show you a transparency about how one proves this. As I said, it was the only way we could see how to study the long-time behavior here without any compactness. Okay, now here's a regularizing effect, which at this point becomes, okay, so the regularizing effect in the stochastic case is that for any lambda in this interval, again, theta is the value of the exponent in the general linearity condition, the measure of the general linearity condition, we can prove that solutions belong to the W in W lambda 1 if you integrate in time, and immediately they become regular for each t. So that's doing a little bit, pushing a little bit more some things we had done with Pierre-Louis and Benoit earlier. Okay, so I will use that later, but for theta 1, this is 5/3, what is that? 4/5, and this 4/5 will come up later in the talk. Okay, now let me talk a little bit about regularizing by noise, and I already showed you regularizing by noise result by telling you that the thing becomes a little bit better. And regularized by noise, okay, that's a canonic. I have to show you something about that, and go back to the result I was describing by Flandoli, Combinelli, and Priola. If I don't have the stochastic term and I start with this initial data, in principle I may get 2 solutions, but by putting a noise in the thing, the regularizing by noise picks up the noise allows you to choose a unique solution. So that's what we have in mind when we talk about regularizing by noise. And so the question we were asking is, what about, can we see something like that rigorously for the stochastic Burger's equation? And the answer to that is we couldn't see it, but we were able to see it at the level of what is known as quasi-solutions. So quasi-solutions was an object that was introduced by Delelis, Otto, and Westenberger some time ago. They were looking at some problem in fluids, and they wanted to write an entropy formulation for the problem, but then was used by the Delelis and Westenberger to test the sharpness of results that one obtains in the kinetic theory, and in particular a result of Benoit with Zabin, which I will mention in a moment. So let me first say what is a quasi-solution. So it's easier to write it at the kinetic level, and so I wrote down the kinetic formulation, and the only difference between quasi-solutions and entropy solutions is that we don't assume anything about the sign of that measure. So it's just a measure. So the assumption is rather weak. It's to claim that distribution here, whatever, is the derivative of some Radon measure. Because we don't assume any assumption on the sign, on the measure, quasi-solutions may not be weak solutions, right? On the other hand, if you have an entropy solution of this problem for some g, then u is a quasi-solution of this zero right-hand side, so it's easy to build them. And also, if you define properly sub and super solutions to the conservation law, which you can do, both of them are quasi-solutions. So it's something you can produce easily. And of course, this is not something you will do. There's no particular reason to do it unless you want to test something. So this is the result for the deterministic case I mentioned by Japan and Benoit. So they proved that the solution is in W lambda 1 for each lambda which is less than a third. This was that I said before in 1D was 4/5 for us. And then Delelis and Westenberger proved that for lambda bigger than a third, you can always construct a quasi-solution which is not in that space. So this way they proved that in that way, I mean, they showed that the results are sharp. And so the question was, for us, is whether noise improves the regularity, or we can do that. Now, I understand this is a very weak test for regularization by noise, but the result I'm going to show you. But also, it's the only result I know for nonlinear problems where you can observe such a phenomenon. And so the result we can prove here is that if we look at the stochastic Burgers, then we proved before that the solutions were in W lambda 1 in 4/5, but we also prove here that the quasi-solution is in that space. So at least the quasi-solutions, by introducing the noise, become better. And again, I understand the quasi-solutions are a weird thing, but at least at the level where before the compactness results you were getting from the estimates you were getting from the kinetic theory failed, here they are there. And the proof is basically the same because we can, okay. Now let me go to this. I mentioned at the beginning, this is going to be a potpourri of a number of papers, the semi-discrete approximations. So this is the problem we want to study up there. I wrote it in as general as I can. And so here's how we're going to approximate it. We're going to do some splitting and a fast relaxation scheme. So we introduce a discretization. At every interval of the discretization, we solve the problem without the measure on the right-hand side. So this is a linear problem we can solve. And then the fast relaxation is that at the end, we project it to make it like 1, 0, 1, or -1, whatever, the chi. So the phi delta t function is discontinuous because we are making this jump at that point. On the other hand, the u deltas we build are continuous in time. Okay? And the result is that at least in the spatially homogeneous case where we have BV bounds, we can get a rate of convergence which is like square root of delta z. I don't know why I changed my notation here. This is supposed to be b. So in the case where b is a Brownian motion, we get a rate of convergence a quarter. So the z is b, the noise I'm using. And so in that case, we get a rate of convergence a quarter for Brownian motion. And when we are in the spatially inhomogeneous setting where we don't know any BV bounds, we can only prove a convergence in L1. Okay. So with the speed I'm going to finish earlier. Ongoing and future problems. Of course, it's if you know a little bit about the theory in the deterministic case, it makes sense to look at this hyperbolic parabolic problem, and that's something that was done earlier by in the deterministic case by Chen and Benoit. So it turns out we can extend the whole theory to that setting. It's just more of a matter of technicalities than anything else. Although we don't know how to do the x-dependent case, because if you know the work in the deterministic case, you have to introduce an additional condition on A, which allows you to do the chain rule. And we don't see how to pass that condition through the limits. And we don't have enough bounds to show that in the deterministic case we can, if we regularize the noise, we can pass that condition down. I think an interesting question to try to see is whether you can develop any kind of numerical schemes, and also whether you can improve the regularity results and the error estimates to become a little bit more, to use the expression that is very popular these days, nearly optimal. Okay, so since I have some time, given the speed I went, I want to show you a little bit how we obtain the rate for the long-time behavior. So the difficulty trying to do kinetic theory for these problems is that the classical approach for kinetic theory was based on taking Fourier transform in space-time, and then use the genuine nonlinearity to get some better regularity. The problem here is that we cannot do anything in time, because we have a highly irregular forcing term. And so some time ago, Boucher and Devillers had looked into a different way to get regularizing effects by not taking Fourier transform in time, but instead regularizing the problem. So I'm just writing here in the deterministic case, so I don't write much. So this is the kinetic formulation before, and then what you do is you add some regularizing operator there, which is, let's say, some fractional Laplacian. And then it doesn't make any difference, the gamma goes, but now this is a regularizing operator, the gamma here, and therefore, if you write formally using variations of constants formula, the solution is given by the linear part, without mu, plus a term that comes from adding the regularizing factor and the measure. And then the idea is to study each of these three terms separately and try to see what you can get for them. All right, so the point here is that if you do that, you split the u, which is the sum of these three things, this, that, and that. You can split it in three parts. One, it's what I call the linear problem. So, it's linear, but doesn't see the m. The second part is that the regularizing operator sees the extra term we added there, the fractional Laplacian. And the third term, which is the most dangerous one, is the one that sees the measure. And the first two are, you can define them pointwise. This is defined in the sense of, in a weak sense. And then you want to study each of these terms separately. And the only place where the genuine nonlinearity condition comes into this elementary lemma, that if you have this integral, and the vector field B you have there is this one, and you put some genuine nonlinearity on that vector field, then in L2 you can obtain that estimate on the solution. So that's some kind of averaging now, and the rate here comes at that place, at that spot. Okay, that's the only place we use the regularizing condition, and then you can look at each one of these terms. So this was what I call the easy term, and for that term we can obtain a bound of that form. This is again where we are using so the theta, the genuine nonlinearity condition, comes on that term. The second term, which again is not difficult, is the one due to the introduction of the regularizing factor. You can control it like that. And the last one sees nothing of all that stuff, just sees the regularizing estimates we have obtained, which in particular case where we use here the lambda Laplacian, it gives you an estimate like that. You put all these things together, and you get a rate. On the other hand, there is nothing to say in the proof that we have done it in the most, in the best possible way, the most, the one that will give you the best rate. And I think it's worth trying to see whether one can improve the rate, given the fact that we know that in the deterministic case, at least in 1 or 2D, it is known that the rate is better. And this proof, if we apply that kind of proof in these two cases, we don't do any better. And we tried several things to play with the gamma and the exponent of the fractional Laplacian, but it doesn't seem to give anything new there. Okay, so I think that's a good time to finish. Thank you very much.